Okay, so good morning, good afternoon, good evening, everyone. My name is Chid Apte. I am chair of the IBM Research Mathematical Sciences Council. On behalf of the Exploratory Sciences program at IBM Research, I would like to welcome you all for attending our first workshop on the informational lens. I think it is safe to say that we are in the midst of a next or new wave of the information revolution, given the rise of AI and quantum computing, and with it, the rapid increase in the use of neurons and qubits as representation and processing elements for information. So to better understand the implications on science and technology, we have assembled together a group of the world's leading scientists to share with us their perspectives of this area. I would like to sincerely thank all our distinguished speakers for agreeing to speak at this workshop, and the workshop program committee for putting together a very exciting agenda. With this, I would like to turn it over to Chaiwa Wu, who is the chair of the program committee that's put together the workshop, to kick off the proceedings. Thank you, and over to you, Chaiwa.
Okay, thank you. So let me share this presentation. Okay, can you see the screen? Okay. So first off, good morning, good afternoon, and good evening, depending on where you're joining us from. So my name is Chaiwa Wu, and I'm a research staff member here at IBM Research. I'm one of the organizers of this workshop, and on behalf of the organizing committee, I would like to welcome you to the inaugural IBM Research workshop on the informational lens. We have an exciting 4 days planned for you with many excellent and exciting talks by leading researchers. Before we dive into the presentation, I'd like to talk a little bit about the purpose of this workshop and how it came to be formed. So the Informational Lens Initiative is an activity, as Tim mentioned, from IBM Research Exploratory Science Program to investigate the linkages between science and technology in areas ranging from neuroscience to quantum computing, from linguistics to coding theory, as viewed to the language and science of information. So yeah, it's all started with what we call the information century that was initiated by two watershed events in the history of science. The first one is Turing's invention in 1936 of a hardware-independent notion of a computing, a universal Turing machine, so to speak, that can emulate any digital computer, and via the Turing church thesis, it can emulate essentially any form of effective computing. On the other hand, in 1948, Claude Shannon formulated the mathematical theory of communication that's independent of their physical form, the how of communication, and even their meaning, the what of communication, abstracting it to a quantitative measure of information in uncertainty in the form of entropy. The notion that this definition is devoid of semantics is not universally accepted, as we will hear from Professor Tishby later on. So these ideas are linked further when Shannon asked about the the least redundant universal Turing machine in terms of the smallest number of internal states. So in 1956, he showed that there's a universal Turing machine with two internal state, and one is not. A UTM with one internal state is not possible. And furthermore, for Neumann and Moore and Shannon, they show that you can actually build reliable logic gates with arbitrary, unreliable logic gates. So since then, many decades of innovation have infused these ideas in almost all modern technological marvel. And so we believe that we're in the midst of another information revolution. So Turing, von Neumann, Shannon, and many others have shown us the importance of the binary digit or the bit, and the advent of qubits and neurons as new representation and processing elements for information, alongside classical bits, has given us new tools, methodology, and challenges to acquire, process, transmit, and store information. So along with the exponential growth in memory and speed of computing machinery, we're witnessing many informational tasks being efficiently performed by computers. So the idea of what we call an informational lens is to view science and technology through the language and science of information. So we see that there are trade-offs and constraints. So for instance, qubit promise massive parallelism, but the decoherence limits their fault tolerance. And similarly, you have biological neurons that operate at relatively low power, but works under limited precision and reliability, and at much lower speed than the modern logic gates that's built with semiconductor technology. So understanding these constraints and trade-off between energy and parallelism versus reliability and speed will have profound consequences throughout technology and sciences. So the goal of this initiative is to identify the state of the art and define where we go next. So in this chart, we sort of list some of the topics that we view through this informational lens. So on one corner, we have the side of bit manipulation, such as error correcting codes, cryptography, compression, the data compression. On the sort of the upper right, we have areas on sort of the foundations and mathematical logic, and these are the mathematical framework that are started by Shannon and Turing and others. On the right, we also have neural network and deep learning, which can be considered as generalization of the Heppian rule, which is defined, by the way, in 1949, around the time that Shannon discovered information theory. On the lower right, we have topics related to sort of artificial natural intelligence. Now, if you look up the Merriam-Webster Online Dictionary, one definition of information is the communication and reception of knowledge or intelligence. So we talk about sort of the information processing via intelligence. On the left side, we have the innovation in quantum information theory and quantum computing. And these are attempts to build viable quantum computing and quantum communication systems. And finally, on the right side, we have sort of the connection between thermodynamics, information, and computing. So at this chart, we sort of shows how these various areas are entangled. No pun intended. Well, actually, pun intended. So we list in these boxes with the blue outline some of the questions we would like to have answered. So in the area of physics, can we build? Oh, actually, that's the wrong chart. So on the physics side, can we build hybrid classical quantum hybrid machines that allow users to solve important problems that we cannot solve today? Can we use the quantum informational lens to understand fundamental physics? On the math side, can we expand the foundations of mathematics using ideas from the informational lens? And on the biology side, can we understand artificial and natural neural networks using the trade-off between energy and reliability? And this chart, and the other boxes, the red, the blue, and the yellow boxes, it's sort of like the linkages between the various components. I'm not going to go over them because many of these topics are actually the subject of the various talks in this workshop. But before I leave this presentation, I'd like to point out some of these recent developments that sort of links back to the two events that we saw at the beginning of the presentation. So this recent paper in January about MIP star equals RE sort of shows that you have these entangled provers that are as powerful as RE, the recursive ennoble set, which is these grammars that are recognizable by Turing machines and thus include the halting problem. So and these are all foundational definitions that dates back all the way to Alan Turing and Alonzo Church. So and then on the blue box, the right side, we have this information bottleneck, and these ideas could be why today we have effort in trying to build limited precision floating point or fixed point arithmetic units and CPU and GPUs, and also analog hardware such as memristors and other type of analog hardware, to try to use them for deep learning. So on the topic of analog computers, ironically, analog computers have existed since antiquity, but they have been sort of supplanted by digital computers after the contribution of Turing, von Neumann, and others. Especially if they have shown us how to deal with noise in the physical world with codes and how to build reliable digital circuits. So analog computers have sort of been relegated to applications where the size, power, and speed make digital implementation unsuitable. For example, like passive audio filter or something like that. So these constraints are being more important now as we are sort of approaching the end of Moore's law. So it's important to see that these development of analog machines are coming back to the forefront. So with that, let's move on to the main event, and let me describe some of the structure of this workshop. So each day we have for each of the 4 days, it will be we sort of follow the same format. We have introduction that sort of outline the theme of the day, followed by a set of presentation, and then followed by Q&A and panel discussion. In the afternoon, will follow by a second set of presentation and a second Q&A panel discussion. Registered attendees should have received an invitation to join Slack, and so we invite them to post questions or comments via Slack at this link here, which you also would have received in your invitation. And by replying to the corresponding thread, so we know what the questions or comment pertains to, and just to to hope that we answer the most important and interesting questions. If you can thumbs up on the question that you'd like to get answered, we'll sort of try to answer them in sequence. So this is sort of a view of the workshop schedule at a glance. So we have 4 days. Today is sort of our quantum theme. Tomorrow we have a theme that's focused on mathematics, computer science, and information theory. Thursday we have a day focused on the theme of biology and AI. And finally, we have a day focused on physics and especially mathematical physics. And so just to list, we have over 500 registered attendees. So I'd like to thank all of you for being here virtually. So here's the sort of a preview of the 4 days. So on day 1, we have themed of a quantum physics theme day with talks on quantum algorithm, quantum information theory, and quantum tomography. The theme for day 2 will be math and CS theme with talks on the foundation of mathematics, which is an area of mathematics that sort of led Turing to develop his theory of computing. And we also have talks on algorithms through the informational lens. For day 3, we will have a biology themed day, and so the topics will be on biology and both natural and artificial intelligence, and we have talks on both deep learning and other building blocks of intelligence. And finally, on day 4, we will have a theme on the physics of information. Especially we have a series of talks on sort of the thermodynamics of information processing in computing. So of course these talks are not neatly separable into themes. So since they're not separable, I guess to reuse a pun, they're entangled. And with that, I'll hand the workshop over to Charles Bennett, who will be the session chair for the morning session.